Hello everyone. Today we're going to talk about a whole new set of numbers. We can say that things are going to get complicated, but don't worry about it. Things aren't as complicated as they seem to be by the name. And I'm going to go with a slow introduction to everything and how we got to this whole new set of numbers. So let's get started. The first thing that I have to talk about is the issue that we stumbled upon when we talked about a root of a number. So the definition of the root of a number, let's say square root of x, is when you square it, you should get the x. And there were a couple of things that came with that whole sentence. First of all, square root of a positive real number x. So x had to be positive real number 0 specifically. And the root itself would also be positive and real number. So this was something that was needed for the definition in order for things to work. And the consequences of that were when we were solving irrational equations, that we had to work with the certain conditions and make sure things worked considering the real set. So everything was considering the real numbers, everything real. And this was specific to second root and not the third root. Third root worked properly and everything was fine. So, mathematicians had issue with that. Why cannot we work with negative values inside of the root? We want to expand and work with everything that's possible. So, let's start with the thing that we were able to do, and there were no issues concerning that, and that was if we worked with, for example, square root of 100. 100 was a positive real number, square root of 100 is a 10, and it is against positive real number, so this is the definition itself. The issue was, as I already said, what if we had square root of minus 100, and that's something that can happen. That's something that when it happened for us, for example, in the irrational equations, we said this doesn't make sense, this doesn't work, so I'm not going to work with that in real set. But this here can appear in mathematics, and simple reason why it can appear is this here equation. We do not know how to solve this equation yet, but let's say that we use the steps that we usually do in order to solve this equation. I want to find or determine the x. So first that would be subtract everything with 100, and x squared is suddenly minus 100, and x squared, which should be in the real set a positive number greater than 0, because square of a real number is always going to be either a positive number or 0, is suddenly equal to a negative value. And this mind-boggled mathematicians, like, what is going on? How can this be? And they, for a long time, assumed that there is nothing, and this is not possible. Because basically what should have happened is that x is either plus or minus 100, root of minus 100, which doesn't make sense for them. Now I'm going back to the example here. Now what we're going to do now is we're going to partially solve this root. What we can actually here root is the 100. So I'm going to group 100 on its own, and it should be multiplied by number minus 1. Now we know from the previous example that I've shown that this is basically 10 times 10 as a square root of 100 times, well, I don't know what to do with minus 1, so I'm going to leave it inside of the root. And here is where we are continuing on into a new set of numbers, something new. What mathematicians decide then? Well, okay, if we work with positive values, if x squared was equal to 100, everything would be fine, no issues there. But let's assume that we can work with negative values, that a square of a number can be equal to a negative value. Now, of course, this doesn't work for real numbers, so we have to expand further on in mathematics add a whole new set of numbers with that if we square, we are going to get then a negative value. The root of the thing, or the root of the whole idea, is in this here example. And it is this. Well, I do not know how much is square root of minus 1. And yeah, we do not know how much is that. So what we're going to do, we are going to define it as its own specific thing. So one thing that was decided and then defined is that we're going to use a special letter I, and we're going to say that this I is going to be equal to square root of minus 1. This I has a name, specific name, and it is going to be called imaginary unit. Imaginary unit. So instead of working with 10 times square root of minus 1, now we're working with 10 times I. Now we are working with 10 times I. And this is a whole new number. And this number is going to be called, since it is with imaginary unit, its name is going to be, or type, imaginary number. Now, if I would put this number instead of the x, I think it would work. Let's show it. Let's see if this is actually correct. So if I use 10i and then square it, let's see how much we're going to get. First of all, I know how much is 10 squared. I can individually square things inside. So this is going to be 100i squared. Now, what is I squared? And this is an important step. Now, if I is equal to minus 1, there is also one consequence that we can now work with, because this is the definition of this imaginary unit, is if I square it, this means I squared is going to be square root of minus 1 squared. Well, I can apply the definition no matter now that x has to be real. Yeah, x is real, by the way. But yeah, I don't care about this part anymore, basically. And this means that I squared is equal to minus 1. Ooh, this is the consequence now. This is another consequence that we're going to work with from now on. So instead of I squared, I can now say this is going to be equal to 100 times minus 1, and this is minus 100. Here we go. Now suddenly things work. Now suddenly square of a number can be negative value. But this number isn't real number. So this doesn't work for the starting assumption and the assumption that we worked with and the definition that we worked with, considering the square root. This is now expanding things with imaginary unit, which is going to be square root of minus 1. And also with imaginary numbers as a new type of number that we didn't deal with before, and they weren't necessary for things that we had and worked with in mathematics before this. Now, what does this do? This gives literally whole new dimensions to mathematics and the numbers in mathematics. Literally. Why am I saying literally, not figuratively? Is because in a couple of lessons, you're going to see that these numbers, these new whole set of numbers, is going to be two-dimensional. Literally. Okay. Now, it was defined. Imaginary unit, imaginary number. Okay, let's continue on. I'm still not doing the complex set, by the way. I'm just defining things in order for the issues or problems that mathematicians stumbled upon, and not just mathematicians, physicists also. I also can presume chemists. I'm not 100% sure though, but I'm 100% sure for the physics that there appeared this similar situation or problem. Now it works. Now let's see how it applies to conventional mathematics. Meaning I want to make sure that basic operations work and see how they work. So let's start with the plus or addition. Let's start with addition and let's show an example of addition. with imaginary numbers. Now I'm using imaginary numbers as they are. Why the name imaginary? Google. So, the example that I'm going to show you is 3i plus 2i. Simple enough. How are we going to add them up? Simple enough. 3i plus 2i is 5i. Probably some of you already figured it out. There are no specifics about it. It is as seen, as normal as it should be. We just apply addition. Let's look at the subtraction. I don't think there are going to be any issues concerning that too. Example, 10i minus 7i. It will be 3i. We are subtracting imaginary numbers, so this is also defined now properly. It works, no issues there. Let's look at the multiplication, and here's where things are gonna get a little bit strange, so to say. 4i times 2i. So I'm multiplying two imaginary numbers and want to see what is going to be the result. Now, if we just look at the I, we can interpret it as a unit. It is a unit. It is a unit, so I can interpret it as, I would interpret unknowns as one little value on its own, or I can also interpret it as a variable, even though it's not a variable. It's a constant. It's constant unit, or its imaginary unit, specifically considering its name and what it is. So what I can do, I can multiply I with I, and I can multiply 4 with 2, as I would. 4 and 2 is equal to 8, and I times I is going to be I squared. Now we already stumbled upon this in the example I've already shown you before. So I'm going to apply this because I want to solve it actually. I want to solve and I want to find the solution. I want to find the product of imaginary numbers. And what we're going to get is, this is 8 times I squared is equal to minus 1. So I'm going to, write down this is minus 1. And this is going to be minus 8. Now look what happened here. With multiplication of two imaginary numbers, as a result, we got real number. As a result, we got a real number. Same thing as the solution to the problem that we had. We got from the imaginary times another imaginary, got a real. So somehow there is a connection, or somehow, I don't know if it's somehow, probably there is a better term to use in this here sense, is there is definite connection between real numbers and imaginary numbers. There's a definite connection. We're going to find it out soon, what it is. I'm still one operation short, and that is the division. So let's find out what is going to be with the division. I'm going to use simple enough example, and it is going to be 18i divided by 9i. We approach this as same as the multiplication, subtraction, or addition. I and I appear in denominator and numerator, so I can cancel them out. What I'm left with is with 18 over 9, and that is 2. Again, division between two imaginary numbers is going to result in real number. There is definite connection. We just don't know the connection and how are imaginary numbers and real numbers connected. Now, one thing is, since there is a connection, one thing that I can now see if it will work is, what if I add up real number with a imaginary number? So let's look at the example. 11 plus pi I. Well, I do not know how to solve it. I do not know how to combine them. So I'm going to leave it as it is. Let's look at the subtraction. In this here case, let's look at the square root of 2 minus 3i. Again, I do not know how to combine them into a number. Now, this is not that I don't know. And this is something that then mathematicians had to work out what's going on here. Can we combine them or not? Or is there anything special around it? Or nothing special or whatever. There are many questions when whole this thing was discovered or made up or whatever you want to say that they've done. So what they decided to do, since there is definite connection between real and imaginary, there's definite connection between these two types, and we can find them, for example, in this here addition or this here subtraction. We do not know how to actually add them up or subtract, but this is a value. This is a value. This is actually a number as a conclusion, but this is something now new. So what they then decided to do is they decided to define a number that consists of both real and imaginary number. Meaning that now we are going to work with a specific number type, for example, z is equal to x plus y I. This is the definition of a number that consists of real and imaginary. This number is going to be called complex number. This is a complex number. Why is it complex? Now we have as a possibility a number, this is a number that is defined by two numbers. Defined by two numbers. And that's important thing. So, this is a complex number, and this number is going to then be part of the complex set. Now let me define the complex set. So z is then element of a complex set, big letter C, sharp C. And let me define the complex set. So numbers that are part of the complex set are numbers that are x plus y I, that look like this, that are combination of two numbers. One is real, one is imaginary, such that x and y are actually real numbers, any real number themselves, those individual parts. Meaning that this 11 is real, pi is real, square root of 2 is real, 3 minus 3, is real. And how can we then see the difference between these two real numbers, x and y? Well, one of them stands alone, the other is with the I. This means that the I, the imaginary unit, tells us what part of the complex number is real and what is the imaginary part. So we are actually now talking about two parts. Let me define the parts. X is going to be the real part of the number. Always the real part. Because it stands alone, it isn't next to I. Meanwhile, y is going to be imaginary part. I am z. Now, look what I'm going to tell you, and this is important thing to note. Y is imaginary part. That's just y. Meantime, y times I is imaginary number. Watch out the difference. If I talk about imaginary number, this means I'm talking about something real times I. If I talk about imaginary number, I'm just talking about a real number that is multiplied with the imaginary unit. We're gonna walk through this, and we're gonna see the difference between two definitions. So, let me show you a couple of examples of these complex now numbers. The numbers that are defined by a real and imaginary number, and real, they have a real part and imaginary part. So, let's look at this. I'm gonna write a couple of complex numbers. Let's start with 1, 2 plus 3i. This is complex number. Now I can of course use these examples too. 11 plus pi I is also complex number. Square root of 2 minus 3i is complex number. Let's continue on. Minus 43 plus I is also complex number. Let's continue on. Minus square root of 5i. It is also a complex number. Not that just it is imaginary number, which it is also a complex number. Why is it complex? Now, why is it? I'm going to go back 2 steps and I'm going to determine parts, and then we're going to see that this number also has 2 parts. Let's go back. So 2 is the real part. Is the real part of this complex number. 3 is imaginary part of this number. Minus 43 is real. Meantime, I seems to be alone. It isn't. Number that multiplies I in that case is is plus 1. So 1 is imaginary part of this number. Now look at this here situation, and we can definitely determine the imaginary part. Imaginary part of minus square root of 5 is minus square root of 5. This is important step. This is just the value that multiplies the imaginary unit. Look at this. Imaginary part is minus square root of 5. What is real though? What is real? Where we don't see anything real, but I can rewrite this down as 0 minus square root of 5. Of course, we're not going to write it down because if we're working with 0, we don't write it down. Similar to when we multiply with 1, we don't write down 1 times something. So real part is actually 0. So imaginary number is also a complex number. Imaginary number is a complex number such that its real part is equal to 0. Let's continue on. I have one more example to show you, or a couple of more examples. 150. Now we know that this is a natural number. Every natural number is also a real number. So this is definitely a real number. But I'm telling you now that it is also a complex number at the same time. If I interpret it like this, 150 plus 0i, I can have 0 for epsilon or y or imaginary part. I can work with a 0. Any real number. This is the definition. Real part is 150. Imaginary part is 0. And this is a complex number too. So this is also complex number. Let's continue on. Pi, it's a real number. It is a complex number. Real part is pi, imaginary part is 0. Minus 1 over 2. It's real number. Real part is minus 1 over 2. Imaginary part is 0. And so on and so on. Meaning all real numbers are at the same time complex. So I can say, before I say what I wanted to say, there's one more thing that we can look at. Are in the same time complex numbers always real? Well, this is an example where we definitely see that this isn't real, because this number consists of the real and imaginary number. This means that the real set is actually a subset of complex numbers. This means all numbers that we know so far are part of this new set, but with whole new extra things and numbers that look like the ones at the beginning of this example. What I can also write down, if I want to show it graphically, this is what we are working with now. So, this is the talk about complex set. There is one more thing that I want to talk about before I end this video, and this is when we talk about these numbers individually. how can we compare them? Greater, lesser. Greater and lesser is going to be an issue for us, and it doesn't concern us that much for now. But what we do want to talk about is the equality of complex numbers. Let's talk about that. So, what are we going to do is this. I'm going to define two complex numbers. Let's say z is x plus yi, and w is another complex number, meaning it has a real and imaginary part. Now I'm going to use different letters, a plus bi. Just so you guys know, the general letters that we use for real imaginary part are real x or a, imaginary y or b. For complex number, we use letters z, w, u, and things like that. So this is something that's common and you're going to see, but we actually do not care. We can use any number that we like or any letter for the numbers that we are working with for in this here examples. But I've decided to use this because they are most common ones. And if these two numbers are equal, this means that x plus yi is equal to a plus bi. This means they are equal. Now, what is actually equal to what? Is the following. Real part is equal to the real part. The real part has to be equal to the real part. Imaginary part, meaning y, also has to be equal to b. Also, they are connected with and. Both of these combos have to work and be true in order for this to be equal. And I'm going to show you one example of this. Simple example enough. Not going to complicate things yet. There's going to be plenty of room for practice of this, and more about it live, already given to you, probably. So look at the example. Let's look at the z, as it is equal to 3 plus 5yi. This is one complex number where we do not know imaginary part what it actually is. And w, it is going to be 2a minus 4i. For complex number w, we do not know actually the real part of that number. Now, the task itself is to determine those parts that are missing or we do not know them if we know that z is equal to w. These two numbers are equal. So let me write it down. 3 plus 5yi is equal to 2a minus 4i. Now let me use the equality of complex numbers, meaning that real number 3 is going to be the real part 2a, and that 5y that is imaginary has to be equal to minus 4 that is imaginary too. So if I divide it by 2, a is going to be 3 over 2. There we go, we found the a. And if I divide here with 5, y is minus 4 over 5. And we determine these values. So if I put these values in, so 5 is going to be times minus 4 over 5. This is going to be minus then 4. Here is minus 4, so this is equal. Let's go with a. 2 times 3 over 2. 2 and 2 are going to cancel each other out. We're left with 3. 3 and 3 here. They are equal. And this is about it for what's new. Let me go back and tell you important things one more time considering the complex set. First of all, we are now working with new numbers. This is imaginary number type and imaginary unit as a new specific unit. It's defined and it is a unit. Addition, subtraction, multiplication, and division work properly, but if we multiply and divide, we can get real numbers as a result from imaginary numbers. There is definite connection, and this connection is going to be set up as a complex number. This is a whole new set of numbers that are defined by two parts. one is real, one is imaginary part, x and y. Or if I look at the bigger picture, real number and imaginary number in a big picture. But important thing is, considering imaginary part or imaginary number, to know the difference. If we talk about the number, this means we're talking about real number times imaginary unit. If we just talk about imaginary part is a real number. This is this y. It is a real number. And it is the number that comes with the I. Basically, the I, or imaginary unit, defines imaginary part of the complex number. When we want to determine things, I would say this is an appropriate way of writing it down. The appropriate way would be that real is 2, imaginary is 3, like in this here example and the following examples that I worked with. So let's work with that. From now on, we can distinguish real and imaginary part. We can distinguish real and imaginary even when we don't see them, like in this example, or with 150 as another example. This doesn't mean that they do not exist. These parts that we don't see still exist, but are 0. These parts are 0. So we can still define them. With first example was real part 0. In the second example, imaginary part was equal to 0. And this is practically it. This is the base of what we're going to talk in the next couple of lessons. We're not going to go too deep into this. We're going to leave complex set and everything considering complex set for 4th grade, when we're going to go and learn some specifics about it, and some actually cool stuff that we get as a consequence from using this set of numbers. See you guys in the next video.